Professor Vikram Kumar, please unmute your mic.
Yeah. Hello?
Yeah.
Yes.
Hello?
Yeah, I've reached.
Yes. Hello?
Yes, hello. Can you hear me?
Yes. Hello?
Hello?
Everything is fine. You have two mics on.
Yeah, Professor Vikram Kumar, you have two mic on. Please unmute your mic. Unmute your mic so we can start.
Hello?
Some echo is coming. Yeah. उनके माइक की कोशिश में है।
You know, when temp is, yeah, 5 minutes before everything.
Hear me now? Actually, I have got two. I've been logged in twice. Hello? Yes.
Now it's okay, sir. Now
It's okay.
Yeah. Okay, so welcome to this second day of this conference. So now we have a plenary lecture from Dr. Chang.
Yes.
I request Professor Vikram Kumar to chair the session. So Professor Vikram Kumar, just let me introduce the chairman of today's plenary session. So Professor Vikram Kumar has been the director of Solid State Physics Laboratory, and after that he was also the director of National Physical Laboratory, and he is the person who basically started the device culture in India, and he is the one who started the first MIC facility in India in which the has been. And after NPL assignment, he joined IIT Delhi as a professor, and now presently he is a emeritus professor at IIT Delhi, and he has contributed very significantly in IIT Delhi also. in creating the nanoelectronics facility, to which Dr. Chang, when you have visited to our facility, you must have seen it. Now I'm just looking to that facility now. So with that introduction, I request Professor Vikram Kumar to chair the session.
Yes, thank you, Dr. Neeraj Khare. It's indeed a pleasure to introduce Professor Edward Chang for this very important and interesting talk. Professor Chang is from the National Chiao Tung University in Hsinchu, Taiwan, and he got his PhD degree from University of Minnesota in 1985. He has worked at Unisys and as well as ComSat laboratories on gallium arsenide MMIC programs. Then he joined National Chiao Tung University and helped set up gallium arsenide MMIC production line in Taiwan. From 1999, he is again at NCTU and currently a Senior Vice President of Research and Development and Dean of International School, the Department of Material Science and Engineering at NCTU. His research interests include new device and process technologies for compound semiconductors and high power electronics applications. He is a fellow Taiwan Material Society and is very wide range interests in semiconductors technologies. So I request Professor to give his talk on Enhancement-Mode gallium nitride FEG-HEMT devices. Thank you, Professor Chang. Please.
Okay, thanks for the introduction. I'm Edward Chang from National Chiao Tung University. I wish I could be in Delhi right now because I have several joint projects with IIT Delhi, and also I have some joint PhD student with IIT Delhi. So I'm so pity that I cannot be in Delhi myself right now to present this material. So my talk will be an enhanced-mode gallium nitride FEG-HEMT device for power switching applications. The FEG means hybrid ferrite charge trap gate stack. Okay, that's our invention, and we use that for EMO device for very high voltage. Okay, so first I give an outline of my talk, give introduction and the material growth of this special stack material, and then device fabrication, and then I show you how it become normally off through this gate stack, and then I also show some demonstration of gallium nitride device for power switching and gate driver applications, and finally I give the conclusion. And first, we know that gallium nitride has become a very popular material and is probably the most important material after silicon, semiconductor material. So, and the reason because the gallium nitride have very high energy band gap and also the electromobility is very high. So it could give you very high current as well and very high breakdown voltage. So this enables gallium nitride to be used for high power and high frequency application for power electronics and for next generation 5G, 6G application. But in this talk, I'll focus on the power applications. So first, give you some idea about gallium nitride HEMT in case you do not know too much about it. Okay, in contrast to silicon device, the gallium nitride HEMT, the semiconductor device does not need any dopant. So in this device, HEMT device, we have gallium nitride, aluminum nitride to form a high band and low band material to form the 2D electron gas. And these 2D electron gas have a very high carrier concentration, okay, due to the surface state, and then very high electromobility, and which give you the very high current. And mostly the material has very high piezoelectric and spontaneous polarization effect, so that can generate a high internal electric field within the material. So this gives you the idea how the material can have high current without doping. Okay, the material, GaN material basically is formed by high band gap air GaN and low band gap GaN. So the material is lack of emerging symmetry over the outside structures. So that create electric field within the material. And this is because the high electron activity of nitrogen atoms. So from here, you can see that the two material, because piezoelectric and spontaneous electric, that generate a high electric field within the structure itself. And then on the surface, there is a lot of donor state on the surface, which give the electrons. So in this way, you generate a lot of electrons from the surface state, and then due to the polarization, electric field, and this electron were driven to the 2DC materials channels. That's why you have high current and also high breakdown voltage for the material. So this is the comparison for the material as a power device. As we know, the structure give a very high current because of the electron, okay, and then density, and then also the band gap give you high electric field. So overall, this material give you a advantage to be used for the power applications. And this compared to the silicon IGBT and silicon carbide, you can see that they give you a much higher breakdown voltage with low specific ohm resistance because of the high current, high carrier concentration within the material. So this is a device, GaN power device, which can be used in a variety of applications, depends on low voltage, medium voltage, and high voltage. So it can replace silicon and some silicon carbide in the range from like 100 to 100 volt to up to more than 1500 volt. Okay, so this is a new material, a new device for power applications. So actually, people are really interested in use this for electric vehicle applications. And there's quite a few company like TI. They have tested this kind of FEG-HEMT for vehicle application, and they have this device have passed all the vehicle reliability tests. So in the car, there's quite a few applications, okay? For example, in the onboard charger, AC-DC onboard charger, AC-DC auxiliary inverter, and DC-DC auxiliary power module, and the charging stations. So these all are possible application field for the gallium nitride HEMT devices. So to achieve this goal, the device have some important requirement. First, the device has high breakdown voltage. It can exceed more than 1000 volt right now with good reliability. And then it has ohm resistance because the dynamic ohm resistance is low because there's quite a lot of current, okay, carriers in the material. And then another thing, if we try to use it for car or vehicle application, we need a normally off, which needs some effort on the device design. Actually, that's the topic of this talk. Okay, and then first let's start with the material. Okay, and gallium nitride, usually to be competitive in the market, they have to grow on silicon because silicon device is very low price. So in this place, okay, first you have to try to grow this gallium nitride on silicon substrate so that can be we know GaN have good performance, but then how about the price? Okay, so you have to grow this on silicon base. And this is the machine we use, okay, on Thomas Wang and Rico Probert. And we did various gases precursors to give us the source, okay, and also some dopant gases, okay. And usually in this kind of new machine, they can handle up to 8 inches, okay. And to grow the material, because the mismatch in the material, okay, that's constant. So you need a lot of tool to monitor the activity during the growth. For example, you have to monitor the growth rate. You have to monitor the refraction, okay, which give you the growth rate and thickness. And then you monitor the curvature, okay, because this give you the strength over the material. If the strength is too high, the material will crack or peel off. And then you need real growth time and uniformity. Okay, so this all can be done by laser sensors. Okay. So the key point here is, of course, first to grow the material, okay, with low stress and good performance and good electrical properties. And one of the difficult part is to grow it for very high breakdown voltage, because we are competing with silicon and silicon carbide. Okay, so you need breakdown up to, hopefully, I mean, can be realized to more than 1200 volt. Okay, to do that, there's quite a few methods. Okay, for example, you can use thicker epitaxial layer. You can use air gain buffer with high band gap, and then with double heterojunction. And then you can use different chaps, dopant chaps, like carbon, like iron, and then you can also use superlattice as a chap, okay, to reduce the leakage current. Those are the common methods used to increase the breakdown voltage of the gallium nitride devices. And then, so this wafer actually we use the Rico new machine. Okay, we can get very good long-to-long reproducibility, and with the structure have a superlattice multi-air gain buffer, and the particle generation is quite low, and we get very uniform thickness and composition uniformity, for example, below 2%, 1%, okay, respectively. And we have a very well controlled bore, even for 6 inch, okay. And then the excellent electrical properties from 1500 to 2000 centimeters square per volt per second. And the voltage, okay, we can get a lateral and vertical breakdown at 900 volt and 600 volt for device applications. So this is the typical structure we use for DMOD devices, okay, with gallium nitride cap, and then air gain with aluminum nitride spacer, and we use superlattice buffer and with some carbon dop, okay. So this is the typical performance if we use air gains is 700 degree volt, and if we use double heterojunction, we can get up to 1100 volt, and if we add the superlattice to it, we can get up to 1500 volt. And there's a picture show you that the crack-free 6-inch gallium nitride epitaxial layer grow on silicon substrate. And this uniformity is actually shear resistance within 1%, mobility in 2.2%, and can up to 1800 centimeters square per volt per second, and shear carrier concentration is only 2.5%. So actually, this just show you this kind of technology is quite applicable to industry already. Okay. And then we show you some of the device fabrication technology. For example, the passivation is very important. So the device start with metal isolation, then ohmic, the gate, passivation, and then interconnects. Okay. And next, an important thing of the epi material device is called current collapse. And this happen because it trapped because the surface electron after surface electron is drift to the 2DEG, then there's a lot of particle ions on the top, and then electron from the gate can be trapped to the surface, and that will deplete your 2DEG. And this is likely to happen if you don't control your surface really well, and this current will start to drop, okay, and then at high drain voltage, the current will drop even more, okay. So this is a current collapse, okay. And this can be, there's quite a few ways to prevent this, and one of these is just use because after the growth, the surface is nitrogen deficient, so you have a lot of nitrogen vacancies, and you have to remove the oxygen bonds and reduce the surface gradient dangling mount, okay, to form the GaN nitride by nitrogen plus plasma treatment, okay. So that will recover your surface stoichiometry of the material, and that will enable you to escape the problem of the current collapse, okay. And this is actually the IV curve, okay, and the breakdown characteristics, which show you that if you're doing this kind of nitrogen treatment to remove the oxide and to recover the surface stoichiometry, you can see that the IDS increase and the SS increase, and also breakdown can be improved, okay. And this is also show you the current collapse, okay. Once your surface is perfect, you don't have charge on the trapping effect, then your current collapse will be reduced. This is compared with the nitrogen passivation and without nitrogen passivation, okay. So you can see its improvement. And also the passivation is very important, okay, because the improper passivation, then you can have current collapse, and you can use like aluminum nitride, PLD, or aluminum oxide, LD type of things, okay. And this is the one we use aluminum nitride plus aluminum oxide, okay. You can see in the layer 2 nanometer aluminum nitride and aluminum oxide, you can get the very small hysteresis, and then also the current collapse is very minimized. Okay, and then the reduction of ohm resistance, you can improve the ohmic contact resistance, okay. So ohmic contact resistance, okay, can be done by regrowth of the GaN nitride, okay, okay, because if you are just by growing and without any dopant, then your ohmic contact works, but the contact resistance is not low. But if you have some regrowth by etching some part away, ohmic area away, and regrow the GaN nitride, then you can get very good contact resistance, okay. And this is the data the technique we use, okay, just by use titanium, aluminum, nickel, gold, and then we regrow the GaN nitride. Then we get a contact resistance is reduced to 0.16, okay, and then the R-ohm is 1.74, okay. And then I go next to, these are the important technology, process technology I just presented, but then the focus of the talk is how to make it normally off, okay. And in the real application, we like normally off, because usually we have depletion mode, and this is normally on, and we need normally off using enhanced mode, because if you are normally on, if you're using the vehicles, then you have to put a voltage on it to turn it off or to shut it off, and for that you need another circuit, okay, and also it's not reliable, okay. So if you can use E mode, you can use simplified circuit, okay, you don't need another voltage, okay, and then you have low power consumption because not in use, the device is off, okay, it's not operating, okay. And then if your device is usually on and you need to put a circuit to make it off, then if the circuit fails, you can have a safety problem. So usually kind of E mode device, okay, is providing is a fail-safe approach. Okay, so that's why we need E-mode devices. But for do that, you still need to have, even with E-mode, there's quite a lot of approach, but you still need to maintain the most important thing is to have high VTH, okay? Because even with E-mode, you can still have failure, because if your VTH is not high enough, if there's a accidental signal, okay, pulse, then your car still can be turned on. So you need to have high enough VTH, usually it's around 2.5 to 3 volt, higher than that. And then you are not going to satisfy other characteristics. For example, you still have high current, you still have very low RO, and you need high breakdown voltage, and then you need low GaN leakage. And on the reliability side, you need a current, you must prevent current collapse, and your VTH must remain stable. Okay, so now those are the issues. Okay, not even you make a E-mode, it means you cannot compensate. You still have to achieve other characteristics. Okay, stand there. And this is just giving you the reason why you need high VTH. Okay, because if your VTH is not high, and if there's a faulty signal coming, then you can turn on the device, and the car will keep on going. So that's a safety issue. So you have to have a very enough high VTH to prevent this happening. And usually there's a few ways that were approached, including like a research gate, okay, to make it smaller, okay, the VTH higher, okay, but current reduced. And you can use PGaN, use PN junction to turn it on, and you can use flooring. Okay, some people use flooring because flooring is the size is about the interstitial size of GaN shell. You can put flooring there, and it's a negative charge. Okay, so you can use that to turn the device off. Okay, so these are a huge approach, but overall it's still could achieve high VTH and high IDS together. Okay, not to say even reliability issues. Okay, here we propose one approach. Okay, we use the ferroelectric. Okay, and the idea is use the ferroelectric to create an internal electric field which is opposed to the electric field you applied. And in that way, when you apply positive voltage, try to turn it off, because the ferroelectric voltage against it. So you have to turn a even higher voltage, put it on a higher even voltage to turn it on. In that way, you increase your VTH. But key point here is you have to have a gas stack, okay, which can generate a charge trapping layer, okay, which will turn your ferroelectric in the right direction. Okay, so this is the right-hand side structure is what we have. We have a tunneling oxide, and then we have a charge trapping oxide, and the tunneling oxide to prevent the charge going away, and on top of that, you have a ferroelectric material to create an electric field. In that way, we can create a enhancement-mode device. That's what we call the ferroelectric charge trapping stack. Okay, so this is the charge trapping material, the ferroelectric material we use, hafnium oxide and hafnium nickel oxide. Okay, and this is formed by ALD with 9 nanometer. Okay, and the good part of this is that this is CMOS compatible. So the technology there, you just apply it to your device. And this must be hafnium nickel oxide, because either hafnium oxide or nickel oxide doesn't have the feature we want. And this is a PE ratio of these characteristics of this material. And the high polarization of 13 microcoulomb per centimeter square can be observed in hafnium nickel oxide. And the original is hafnium nickel oxide is amorphous, and you can anneal it, and then it can form this kind of polarization, and this is not observed in hafnium oxide alone. Okay. So this is the device fabrication. So you just like the regular one we did. Okay, we use ohmic and mesa, and then we use harmonic oxide. Okay, this a huge device for comparison, but because time is limited, so I'm not going to go through the other device, but I'm just showing the one we use for harmonic oxide. And this device A is some others. Okay, let's keep this. Okay, and okay, this harmonic oxide. The only one I'm going to present is harmonic oxide. Okay, is give a very high VTH 4.4 volt and very high current of 770 milliamp per millimeter. And then if you compare to the other technology, okay, we also fabricate other devices or other technology. And you can see that ferroelectric FEG-HEMT give you a 770 milliamp per millimeter, which is very high. And VTH is 4.4 volt and R ohm is around 10 ohm per millimeter. Breakdown voltage is 1100 and subthreshold voltage is 100 and hysteresis is more. Okay, so and that's the feature of the device. And then this is how it turn on. You can initiate the 12 volt for 1 second and you get polarization. You can charge in harmonic oxide and then you put a polarization. And after initiation, the larger concentration in charge storage layer is remain there, and the polarization for the ferroelectric remain there, and the blocking layer. Okay, the blocking layer will keep the charge in the charge storage layers. Okay. And this is show you the IV curve of this device after initiation. So you can see after initiation, more electron trapped in the gate oxide. Okay, the first force applied to create oxide, charging oxide, and then you use ferroelectric, and you turn the gate voltage on. Okay, to make it really become an E-mode. Okay, and then using this approach, you can see that you can get a very high VTH and with high current. Usually, the high VTH come out with the sacrifice in the current, but in this case, your current remain the same because you did not touch anything in the channel region. Okay. Okay, so that's the approach. But then you can further increase the on resistance, very low on resistance and very low channel resistance and high breakdown. Okay, so how can you do that? Okay, because the channel resistance need to be decreased too. Okay, so in this way we use the thin structures. Okay, tri-gate. Okay, so the tri-gate structure with nanowire about 100 nanometer, because 100 nanometer enable you to deplete the channel. Okay, so it become E-mode. Okay, and also because this you can have you have the 2DC and you have the inversion layer on the gate sidewall, and then you can make very low channel resistance. Okay, so in this way we have multi nanowires. Okay, to create enough current. Okay, and this is the structure that you can use. We use several harmonic oxide layer with aluminum oxide insert between, so you can get with these small layers you can get enough ferroelectric electric field and enough current. Okay, and okay, this is more detailed structure of like this. And so by this approach, you have tri-gate structures which give you low channel resistance, and you have ferroelectric gate stack which give you high VTH and high current. And overall, you get what the ideal device for high breakdown, high current, and low channel resistance. Okay, so this is the device. Okay, top view, overall scope. Okay, and then and this. Okay, this gives you the idea, and this is the cross section of the. It had to be. Length wire must be 100 nanometer. Okay, or less. Okay. And this is the tri-gate, okay, device performance. Okay, you can get with VTH, and also I think this approach, the important thing is your channel risk will be really reduced. So you get all the characteristics you want for E-mode device. Okay. So this tri-gate device, we have more 896 milliamp per millimeter and very low ROhm. Okay. And this is the comparison of the device with any published data on this kind of HEMT devices. Okay, so we get very low channel resistance. Okay, and to do that, you just like I mentioned, your narrow wire, okay, must be 100 nano or below, so you can turn everything off. And the breakdown is also good enough, around 7 to 800 volt. So actually, this is by far, if you benchmark against other devices, this is the all characteristics meet, and is by far probably the best performance. Okay. Okay. And okay, that's fine. Okay. And the next thing I show you demonstrate some real applications. Okay. So this is the 120 millimeter gallium nitride HEMT devices, and it is output 60 amp and breakdown is more than 1200 volt. And this is a fabrication, okay, the device fabricate. And we have used for power modules, okay, and for various applications. So we have demonstrated silicon wave from wafer level to module level, okay. And we use for some boost converter, okay, and we show that the use GaN, okay, the power use is much less than use MOSFET, okay. And also some other switching devices. Okay. Okay. Oh, yeah. So this is for power for solar panel. We use for solar panel. Okay. Thank you. Okay. And finally, I can show that this kind of gallium nitride approach, you can make it really compact. Okay, because the gallium nitride have high mobility, so it can operate at higher frequency. And because higher frequency, your inductor can be reduced, so your size can be very compact. Okay. So this is we use as a gallium nitride MMIC, and then we use that for the driver technology. Okay. And originally the size, okay, and the right hand side is you use chip, the gate driver IC can be really reduced. So this can be because the high frequency, high mobility, high frequency, and then you increase the mixer rectifier VCO altogether. Okay, so you get it very small. Okay, so actually you can see on the top, the size of the converter is that's that big. But if you make it in a MMIC, then the size is about 1/100. Okay, and we also make for some wireless charger. Okay, let's skip this because it too. Okay, we use this kind of same device for wireless charger. Okay, maybe just we can charge 140 centimeter. Okay, and it's 50 centimeter. The charging efficiency is 95%. Okay. So so I have shown that the gallium nitride electronics is maybe a very important power switching system application. Okay, but it's just starting. Okay, because mostly because of price issue and the reliability issue, but it's getting there. And then we propose a gallium nitride FEG-HEMT structures, which can be used for E-mode device, and this is a new concept. Okay, and this device have all the important characteristics. For example, high breakdown voltage, high electric field, high current, and low channel resistance, low ROhm. Okay, so this is ideal for E-mode application. Okay, and we have used this to demonstrate quite a few different applications. Okay. So, okay, that's my presentation materials. If you have any questions, yeah.
Thank you, Professor Chan. Hello, am I audible?
Yes.
Okay. Thank you for the excellent talk, giving an overview of gallium nitride technology and also device applications for, especially for electric vehicles. Now, let me see if there are any questions in the chat box. There don't seem to be any. So I will just ask a small question. You have used ferroelectric charge trap. So what is about the choice of ferroelectric material? How do you choose this ferroelectric material?
How do you choose the property? How do you choose? Oh, because of ferroelectric, you have
the material.
First, you must be CMOS compatible. You must have two thin film, and then you have a good polarization, enough high polarization and compatible with the process we have, and the material compatibility, because you grow it on GaN nitride, and the interface maybe another charge type of things. Then you have other hysteresis, those type of things. So you have overall you have to choose a thin film and the CMOS compatible and compatible GaN nitride too with high polarization.
So what is the choice? I mean, which are the materials which are candidates for this?
What material candidates? Actually, we select quite a few. This is the only one we think it will work because this material is widely used in the memory. So their process and reliability is already proven in memory. Okay, memory devices.
Okay. Not much else. Okay, so
Professor Vikram Kumar, there is one, sir, there is one question that about the ferroelectric materials again, that what is the criteria, which ferroelectric materials will be used?
Yeah, that's something I asked.
Yeah, okay. Right.
That was my question also. But I don't see anything in the chat box.
Yeah, there is, sir. I don't know why it's not visible to you. It should be. There is one more question that the nanowire width is changed and what is going to happen in the device?
What will happen with changing nanowire width?
Yes.
Nanowire?
Yes.
You mean which one? This one. Oh, if it's too big, then you cannot pinch off. Okay, you cannot deplete because the nanowire has to be below 100. Otherwise, the depletion field, the built-in field cannot deplete the channel, and then it cannot be E-mode. Okay, so choose the width because the built-in potential can deplete the channel to DC. Okay, that's the criteria. Yeah.
Okay, sir. Thank you.
Okay. So once again, we thank Professor Chang.
Yes.
And I think we.
Okay.
Thank you. Thank you.
Thank you. I hope I can come back to India quick because I have quite a few joint students there. Yeah.
Thank you, Professor Vikram Kumar, for chairing this session. And it's very well finished, very well in time, so that we can start the second plenary speaker. And thank you very much, Dr. Chang, for accepting our invitation. Of course, we have a lot of association with IIT Delhi and your institute, and you have been a pioneer in establishing that bridge. So we are very much thankful to you for that also. And hopefully we will have more strong collaboration with your institute and from IIT Delhi in future. Thank you very much, sir.
Thank you. Thank you very much. Yeah.
So now I move to the second plenary lecture of today morning session. And the speaker is Professor Subet Meliskar from Nanyang Technology University, Singapore. thank you very much, Professor Subed, for accepting our invitation. In fact, we wrote to you, and just in half a day, we got your acceptance for that. So we feel very happy to see your acceptance for giving this talk. So let me give a brief introduction of Professor Subed. And he did his graduation from IIT Bombay, and after that PhD from Ohio State University. And he joined the NTU Singapore in 2001. And earlier to that, almost like 10 years, he spent in microelectronic industry. And currently at Nanyang Technology University, Singapore, he is a President Chair Professor in Energy. And also he is Associate Vice President Energy and Executive Director of the Energy Research Institute. His research is in the area of semiconductor technology, perovskite solar cells, printed electronics, and energy storage. So he's the right person on this platform to give a talk on. He's going to talk on thermally cooperated large area perovskite solar cells and mini modules for tandem integration. So, Professor Subed.
Thank you, Professor Khare. Can you hear me all right?
Yeah, we can hear you. Yeah.
Okay. Let me start sharing my screen. Okay.
Yes, it's visible.
Can you see my screen?
Yes, it is visible.
Is it in a complete slideshow mode? Is it full screen?
Yeah, now it's a complete slide mode.
Okay, all right.
Yeah.
So it's really my pleasure to share our work on perovskites. I note that the previous presentation by Professor Chang was on gallium nitride. That is something that we work on also, not myself, but some of my colleagues work on, and there was a very interesting talk. What I'll focus on is a completely different topic, and that's on perovskites. Before I get into the perovskite details, I thought I'll just show you a couple of slides in terms of background. I think silicon and solar cells in general have done an amazing job. And as you can see, beginning 2010, when it was more than 50 cents per kilowatt, now we are already hitting less than 10 cents per kilowatt in terms of residential solar. Of course, the goal for 2030 is 5 cents. But as most of us know, in utility solar, especially with solar farms, we are already hitting the 5 cents per kilowatt goal or even below. Solar cells have made really an amazing progress over beginning 1954 onwards, when panels began to be made. And not only that, the wattage per panel has improved very significantly. This has been really driven by the efficiency improvement in the solar panels, in the solar cell itself. What one would appreciate is efficiencies, maximization of efficiencies is essential. Not just from a cost perspective, but as I'll share with you later on as well, very often space is limited in cities. And that is essentially really one of the requirements in terms of kilowatt hour per meter square. Maximization of that is essential because of limited rooftop space. Most of our demand for solar is in cities. So heading that way is a priority for most companies as well as most cities. Most of you are aware that perovskites basically started from nowhere, somewhere in the range of 2009 to 2012. And over the past 8 years or so, we have hit efficiencies of more than 25.5% in fully solution perovskite solar cells. And you can really see this over here, where you can see the 25.5% efficiencies of perovskites on the right-hand side. And it is not that far away from silicon, which is 26.1, or heterojunction silicon, which is 26.7. Of course, one has to understand that these are champion efficiencies, and really we are speaking of devices which are less than 1 centimeter square for single junction, and for tandem, very often the scale is also in similar range. So before I get into the details, for some of you who are not subject matter experts in this area, perovskites are really a structure that is borrowed from calcium titanate. And in this case, you have octahedra, which is made of PbI6, and you have different groups that can sit in the in the cavities of these edge-connected octahedras. The materials which are possible that can sit in these, methyl ammonium, include other forms of organic, inorganic hybrids, or you can even have cesium to form more or less an inorganic perovskite. One of the key attributes of perovskites is it can be completely done in solution processing. And as you can see in this schematic on the right hand side, you can start with deposition of lead iodide and convert it using methyl ammonium iodide to methyl ammonium lead iodide perovskites. And this process can be done at less than 100 degrees centigrade. One of the key advantages of this is this can be done with, really paper thin. It could be done roll to roll processing. This process can also be done using evaporated processes, which a lot of silicon processing companies are familiar with. And definitely this also is amenable for deposition on plastics and making it flexible. So these are the kind of things that we began working on, and we were very at the right place at the right time, and we began working on it beginning 2012. Over the last 8 years, we've done a lot of fundamental work explaining why perovskites are phenomenal semiconductors, both in terms of charge transport as well as in terms of light emission. We have worked on inorganic materials, flexible materials, different types of water splitting. We've done a fair amount of work on hot carrier cooling as well as multi-photon absorption as well. And most of these works are readily accessible. What is exciting in perovskites is really the possibility of the structural diversity of this material, and you can tune the emission, you can tune the optoelectronic properties as well as stability using different configurations of perovskites itself. This is even further extended by the possibility of substitutions, chemical substitutions, elemental substitutions. And you can have metal deficient perovskites, variety of layered or dimer perovskites, as well as double perovskites. It's estimated that this variation in composition as well as in structure leads to more than tens of millions of possible combinations of perovskites. And that's why a lot of work is also now being done in using artificial intelligence or machine learning in designing of these materials. Further complexity can be also introduced by the possibility of nanostructuring. You can make perovskites into nanoplates, nanorods, nanoparticles, and even core shell nanoparticles. And this also gives really a full range of spectral tunability as well as very high photoluminescent quantum yields can be obtained by these quantum dots or nanoparticles. One of the significant attributes of this is, of course, it can be deposited by very simple techniques like a squeegee printing type, screen printing type technique. And I'll touch upon that a little bit. When it comes to large area processing, this is some of the work that we have done in the lab. We have put down screen printing processes. We do a fair amount of slot die coating. The image on the left-hand side is samples which are 5 to 10 centimeter squares in size. Then you can assemble them into panels, and you can see a 3x3 matrix here of 10 by 10 centimeter devices. We have the largest we have done so far is a 30 centimeter by 30 centimeter device, and you can see an entire hand behind these stripes of perovskites that have been deposited. There's a lot of work that has gone on in really single step deposition of perovskites, and by again controlling the stripe width, you can make these devices almost semi-transparent. I'll also share with you later on how controlling the thickness and controlling and converting each of the electrodes to transparent electrodes, you can also make semi-transparent perovskites as well. So this is a broad explanation of what perovskites can do. We recently have set up a joint venture with Singapore Safety Glass, and this allows us the possibility of extending the work we have done almost into a batik printing type process, where we can take a 30 by 30 print and print on large scale glass multiple times to make solar windows, for example. At this point, most of the work that we are doing is really based on carbon-based materials. So these are not really transparent, but as I said, I'll touch upon that later on as well. Some of the things that we are venturing into is deposition of perovskites over, as you can see on the panel in the bottom. This is a piece of glass which is 2 meters by 3 meters, and it takes 3 or 4 people to put the glass in place. And this is essentially our tools for screen printing, for laser scribing, cleaning, as well as processing of perovskite window glass. So these are the kind of work that is ongoing. Of course, the ultimate is integrating this with colorful building integrated photovoltaics. And this is an image, a photograph that I took in the Swiss Tech Center. The panels that you see in the background are dye-sensitized solar cells. And of course, the efficiency of these solar cells is less than 5% in this format. So really the vision or the opportunity is, can you make semi-transparent perovskites in this scale with efficiencies exceeding 15%? And if that can happen, I think that would really be a game changer in terms of what we can do with building integrated photovoltaics. Having said that, one of the key motivations that we also have beyond building integrated photovoltaics is to see what can we do from the perspective of making silicon better. Why do we need to improve silicon? This is a photograph of Nanyang Technological University, NTU, where we have installed 5 megawatts of solar. Unfortunately, even by covering every rooftop, we can only generate less than 5% of the electricity that one needs on a typical day. So the only way to increase the amount of output from such a campus is to transition towards technologies that give you greater kilowatt hour per meter square. And this would really, as I mentioned earlier, be a game changer from the perspective of what would happen in cities. Of course, silicon photovoltaics has done a phenomenal job over the last decade, and no longer can one say that silicon solar cells are expensive. Efficiencies as well as long-term stabilities have always been maximized from the silicon solar perspective. But I think practically everyone acknowledges that we are close to reaching the practical solar efficiency limit of silicon. And that's really why new approaches need to be considered. The approach that I'm going to focus on today is going to be that of tandem solar cells. And in this concept, one would couple the possibility of multiple absorbers working in tandem with each other. So the possibility of a blue absorbing perovskite that can be coupled with the output of a silicon solar cell is extremely appealing, because as I'll show you, this really gives the possibility of surpassing the silicon solar cell limit. The limit of silicon solar cells more or less is acknowledged to be in the range of 29.4%. The theoretical limit of perovskite silicon tandems, however, can be as high as 43%. To date, perovskites have hit 25.5% in single junction, but in two terminal as well as 4 terminal, the efficiencies of 29.15% have been demonstrated. So in today's presentation, I will start off with the evaporated approach towards tandem solar cells, but I will have maybe a couple of slides later on to also talk about solution processed approach that can also be used for tandem solar cells. The efficiency needs to be maximized by choosing the right material sets for the perovskites, where the band gap of the perovskite has a huge impact. So the band gap of the perovskites and the band gap of the silicon need to be properly chosen in order to maximize the performance of these devices. So here we work on both the 2-terminal as well as 4-terminal solar cells, and the challenges in each one of them is quite different. Of course, in the 4-terminal, the challenge includes the challenge of having 2 separate solar cells and increasing the power electronics that can be coupled with it. So the 4-terminal already, although is simpler, is more complicated from a electronic or a coupling perspective. On the other hand, it's the 2-terminal, its own complexities. One needs to make sure that the silicon is properly tuned so as to maximize the absorption in the infrared range. Then the entire stack that starts essentially with the recombination layers, as well as the transparent conducting oxides, the perovskite material itself, the whole transporting layers, and perhaps also the anti-reflection coatings needs to be optimized as well. From a fill factor perspective, you also need to take care of the electrodes and ensure maximization of the fill factor. I will touch upon this in some of my slides. So we began working on vacuum deposition primarily because at that point, one of the major challenges was conformal coatings on silicon surfaces that have been really tuned for maximizing, essentially for optical control. The other major advantage of evaporated materials is they are free of solvents. And if they're free of solvents, the argument is they should be more stable than solution processed materials. And we will investigate this factor later on. Typically, you would have multiple sources for evaporators, and co-evaporation can be done by to form the perovskites in situ. So in our process, we really started off identifying each of the materials that needs to be deposited. I seem to be missing one slide. So the first step in this is really active layer engineering, where you choose the deposition of the materials. In our case, we essentially fix the deposition of lead iodide and change the temperature for the deposition of methyl ammonium iodide, and we found out that the optimal is in the range of about 100 degrees. After the deposition of the active layers is done, the next step would be interfacial optimization, and this is where the different combinations of either tin oxide or tin oxide and PCBM or titanium oxide need to be tuned. And this is essentially highlighting the role of thin layers of PCBM, where the tin oxide PCBM complex or the tin oxide PCBM hybrid can be a better carrier selective interface to maximize performance of solar cells. And that became the first step that took care of interfacial optimization. After that was done, a surface treatment was needed, and the surface treatment was needed. The identified surface treatment included methyl ammonium iodide as well as potassium acetate, and this allowed really to compensate, to neutralize a lot of the defects that were present in the bulk perovskite. It also helped improve the grain boundary conductivity of the deposited films, and this was verified by transient photoluminescence as well as transient absorption. And here you can see really that in the treated samples, which are on the right hand side, you can see a long-lived photo bleach excitation at 717 nanometers. We could also confirm the presence of potassium in the perovskite by using top sims. So really the main takeaway message from this is you need to optimize the active layer, the interfaces, as well as the surface treatment. So let's take a look at how these translates into efficiency gains in the solar cells. So the AGS deposited methyl ammonium lead iodide gave us about 19.13% and certain level of hysteresis. As we do the treatment of these materials, you could see that the hysteresis was suppressed, and more or less the VOC and as well as the JSC did not change a whole lot. One of the factors that did affect is the fill factor. Further deposition of lithium fluoride to form the anti-reflection coating really gave us efficiencies in excess of 20.28%. And as you can see from this graph, not only the efficiencies improved, we also had better control in terms of the range of solar cells that were obtained. So the step-by-step optimization is essential in the deposition of these materials. The next question that we also had to understand was from the stability perspective. And all the data I'm showing you today is materials which do not have any encapsulation. So these are unencapsulated solar cells. And what I'm showing you in this graph is solar cells that have been held for more than 100 hours at MPPT with a relative humidity of 70 degrees in our environment. We also studied unencapsulated cells at room temperature and a slightly lower relative humidity. And here we have studied cells that have really been held for more than 500 hours and with PCEs of over 90%. As I'll highlight to you later on, this is really a special factor from an intrinsic stability of evaporated perovskites. But I'll come to that in just a minute. In addition to room temperature studies, we also expose these perovskites to higher temperatures, and in this case, 85 degrees centigrade, and these samples were also unencapsulated. These were stored in this condition for more than 3,600 hours throughout the lockdowns that we had this year because of COVID. And as you can see, there is a certain level of degradation, but the degradation is not as significant as has been seen with solution process device, as I'll also share with you on the next slide. So the PCE of more than 80% could be retained for more than 5 months. So the question we began asking is what are the factors that are contributing to this performance? And we also wanted to compare this evaporated stability with stability of solution process devices. And as you can see, the pink dots is the stability of the evaporated devices, whereas the stability of spin-coated devices really very rapidly degrades upon storage or exposure. So this stability of the NIP, methyl aluminum lead iodide, is also notable because we are using Spiro as a whole transport material. Spiro has been known to cause degradation in solar cell from a stability perspective as well. This material that we am showing you in terms of its degradation is a multi-cation perovskite, and we really did also want to just rule out any other factors. And here I'm showing you the performance of methyl ammonium lead iodide and comparing it with the equivalent performance of these of the evaporated perovskite solar cells. So the one of the main reasons that we believe that the stability of the solution process device degrades is because of interfacial issues. I think from the analysis that we have done, we see increased recombination, and that is the main cause in terms of degradation of methyl ammonium lead iodide. So really the key question that we would like to ask and respond to is it the composition or is it the process? And from what we have seen, we believe that it is really the structure of the material which is deposited by evaporated perovskites that gives us better stability. So the different growth processes is critical, and I'm not showing all the materials characterization data, but that is one of the key factors in terms of how the material gets deposited. So just to zoom in a little bit on the 85-degree performance, what we see is at about 1200 hours, there's practically no change in the perovskite itself. But as the perovskite is stored at 85C for 3000 plus hours, you begin to see degradation at the edges. And it's really the edge-based issues that we need to tackle. As you can also see in these images, there really is not a significant change in terms of the perovskite material itself, but most of the changes are happening from the perspective of the edges of these devices. We also took a slightly closer look in comparing these devices from a JSC perspective. As a EQE perspective, you can see that there really isn't any significant change. There is a slight degradation, but more or less the performance of these devices speaks for itself. There, however, clearly, as you can see from the impedance analysis, there is increased recombination. We also looked at these devices in terms of MPPT tracking, and even after 3,600 hours of exposure to high temperature, the MPPT performance over hundreds of minutes wasn't too bad. So the main takeaway message with this is there is significant differences in the stability of evaporated devices as opposed to devices which are solution processed. Just to compare, so far the data that I've shown you has been more with the PIN devices. Most of the so far I've shown you is more mainly with the NIP devices. Most of the PIN devices, which are with the darker blue colors, have performed slightly better than the NIP devices, and it is exactly the same finding that we have in our study as well. In this slide, I'm showing the performance of the champion PIN devices, and we have worked on this with several different hole transporting materials. In our case, we see a slight better performance with Spiro, which is evaporated, as opposed to PTAA that was deposited as well. And I think these are the kind of experiments which are still ongoing, and all the work in terms of the PIN structures has not been completed yet. But at the same time, we do begin ask the question in terms of scaling. As I said earlier, the focus of this work is really tandem solar cells, and we would like to deposit these materials on 6-inch silicon substrates. And that is why the transition from small spot cells to test cells, as well as stripes, and eventually mini modules, is what I'll share over the next few slides. So from a scaling perspective, we do drop a little bit from 20.27% to about 17+% as you go to 2 centimeters square. And this is something that needs a lot more study. We have also tried a deposition of these same stacks on flexible substrates. And we are also very encouraged that even on deposition with flexible substrates, the overall efficiencies also is maintained. The stabilized power output is also unchanged with time with these flexible devices. So this also raises the possibility of perovskite tandems that could be deposited on flexible substrates, and that is a topic that we would touch upon in the years to come. Coming back to the long-term stability discussion, we also looked at the long-term stability of these devices, and similar to what we have seen with the NIP, the PIN structures also are quite stable. And I think this is definitely something that needs to be exploited. Coming back to the discussion in terms of towards large area deposition, I think in this case, I'm showing you the transition from about 0.16 centimeter square to 4 centimeter square. One of the things we noticed as we went larger in size, again, as you can see from this graph, you really do not see very significant differences in terms of the current or the VOCs. What you do see a significant drop in is the fill factor. So we decided to study this factor a little bit more. And in the first experiment, we essentially held the length of the stripes constant, and we varied the width of each of these stripes. What we observed is that if the stripe size, if the stripe width, I should say, is in the range of 0.25 centimeters, you really do not have very significant changes in terms of the fill factor. So in the next study, we fixed the width of this device to 0.65 centimeters, and we varied the length of this. And as you can see, for this fixed width, there really wasn't a very large difference in terms of the fill factor as you go from a shorter length to a longer length in terms of these devices. And from these studies really helped us define the design rules in terms of stripe sizes that we will make into modules, which I'm sharing in the subsequent slides. But before you go on to the modules, one of the other questions to also answer is if these need to be integrated with silicon, you really need to take into account the possibility of semi-transparent solar cells. So far, the cell structure that I've shared with you has gold on it. So we really had to replace the gold. And in this case, we replaced the gold with a very thin layer of silver and an ITO deposition on top of it. In one of the studies, we also changed the thickness of the ITO so that by changing the thickness, one could also change the conductivity or the resistance of the ITO. And what we noticed, not entirely unexpectedly, is that the reflectance of this stack would change. And very interestingly, by changing the thickness of the ITO, we could also generate colors that could really start with a light green all the way to a darker green, cyan, pink, and everything in between. And if you can put these colors on a CIE map, you really can see that you can control the color of this glass extremely well, and that you can do that by changing the thickness without compromising the efficiency of these devices. So the efficiencies of these colored solar cells was maintained in the range of 11.22%, even when we started making mini modules of the size of 16 centimeters square. And again, this would be very appealing from a building integrated photovoltaics perspective, that you can get a gamut of colors by controlling the thickness of the individual layers. What we had not completed, and this is work which is ongoing, is for making mini modules, you really need to come up with different processes that could take care of the individual scribing of the ITO as well as the active layer. And this scribing, we began doing. The P1 in this case was done with laser, and the P2 and P3 was done manually. And we have made mini modules that range from sizes of about 14 to 47 centimeters square. And as you can see in this histogram, the distribution is not bad. The largest modules give us in excess of 16 to 17%, as you can see over here, with very decent VOCs, JSCs, as well as fill factors. At this point, the evaporator that we have limits us to a maximum size of about 40 to 50 centimeters square. And we are in the process of commissioning a new tool that will allow us compatibility with more than 250 centimeters square or 6-inch substrates. But before we get there and scale, we really have continued to work on optimization of the mini modules. And now we have just implemented a full laser process where we scribe all the individual layers using lasers. And with this, we have been able to increase the geometric fill factors to the 92% range, and PCEs for a 6 centimeter plus device is in excess of 18%. So far I've been really speaking about evaporator devices, and really the main takeaway I want to leave from the presentation so far is stability perspective. There is something different in terms of the thermal evaporation as opposed to other processes, and you have an intrinsic stability which is possible with this process. From a scalability perspective, we have shown PCEs of more than 18% on 21 centimeter square devices, and this probably is one of the highest in terms of size compared to all the other solution processed, hybrid, or CVD, PVD processes as well. What I'm also showing on the right-hand side over here is what can we estimate the performance of these devices when we scale to 6-inch. And from these red stars is our data. As we scale, you can see that the evaporated solar cells do drop a little bit, but do not drop as high as you can see the drop in terms of solution process. The solution process devices, the drop is much steeper. So really, we are intending that when we scale up to 6-inch, we would really like to target high performance, and what that high performance would look like, I will also touch upon in the slides to come. So what I have shared with you so far is really both the PIN and NIP structures, and these have been deposited using a fixed temperature of PBI2, and now also a fixed temperature of methyl ammonium of 100 degrees. The next thing we began looking at is it feasible to make tandem cells also solution processing? And in the solution processing aspect, we have been working on slot die coating. The slot die coating process that we worked on really takes different precursors, adds a variety of different additives, as I'll share with you later on as well. And the slot die head and an air knife move in unison with each other. And the coating area that we are again limited to is at this point 100 centimeters square. This is ongoing work as well. Similar to what we have done with evaporated materials, we also had to work a fair amount on the optimization and the additives that would go into the slot die coating devices. And as you can see here, we really had to take care of compensating for materials like cesium, Fa, and potassium, just like in evaporated perovskites, also seem to play a role. And consistently, I think we can get efficiencies in excess of 19%. Similar to what we've done with evaporated cells, we also worked on scaling up as well as mini modules. And this mini module that I'm sharing with you is almost 60 centimeters square. And at 60 centimeters square, we can get efficiencies in excess of 19%. So similar to evaporated perovskites, you really had to take care of etching for the first for all of the three layers, and the proper design of each of these stripes is important subsequently from the perspective of tandem solar cells. So I actually did not include any tandem data so far. What we have completed in the lab so far is for 4-terminal tandems, we can get efficiencies in the range of 26.5. And for 2-terminal tandems, we are getting efficiencies which are in the range of 18 to 20%. Most of our challenge so far has been in terms of matching the performance of the perovskites with matching the performance of silicon. So really the question that we're asking is, what is the roadmap towards 30% perovskite silicon solar cells? So the first step really is to change or increase the VOC from about 1.7 to 1.9. And what is essential there is new materials in terms of perovskites that will give you a band gap of about 1.7. What is also essential is to work on the silicon bottom cell and to push the VOC of silicon bottom cell to more than 0.7% and to look at different recombination layers. The other aspect to work on is to push the JC to 20 milliamps per centimeter square, and this needs to be done by changing the PIN, changing to the PIN configuration, thinning the individual layers, making sure that you really have no parasitic absorptions in the other layers, and also to work on higher performance of silicon, especially in the IR range. What would be needed is silicon bottom cells that can give you a JC of more than 20. Lastly, what is needed is to really push forward with the fill factors as well. And this needs to look at a variety of interfacial engineering as well as metal fingers design and different types of texturing from an optical management perspective. In the last couple of slides, I just want to address some of the other pressing issues that always are asked in terms of perovskites. Always the question comes up, hey, but what about the lead? And this graphic really shows you that yes, perovskites have lead, but so does silicon modules, and so does really the soil that naturally occurs all over the planet. So more or less, there's a lot of work ongoing on lead-free perovskites, but I think increasing the focus right now is completely from the perspective of maximizing the performance of the perovskite lead-based solar cells for now. From a stability perspective, we have been leveraging a lot of work that has gone in silicon. I think most of you know that silicon solar cells by itself are not stable either, and you really need a fair amount of encapsulation as well as from a UV perspective to make sure the stability can be met. We have been doing a fair amount of work on stability, but there has been several publications where all the IEC tests that the silicon has passed, a most number of perovskite configurations have also been passing most of the IEC tests. The records and the scale-up efforts that are reported so far is Panasonic is reported to have demonstrated an 800 centimeter square panel with efficiencies of more than 16%. There are several companies in China and other parts of the world that are targeting efficiencies of more than 17% for 900 square centimeters in terms of size. Of course, this is a sample which has been demonstrated by Oxford PV. So really a lot of work is ongoing in terms of scaling of these devices. I didn't get time to cover this today, but an excellent absorber is an excellent emitter, and perovskites are no different. And just to take one graph, perovskites have, over the last 5 years, have demonstrated performance which is very much on par with quantum dot based LEDs, and which is not that far off from organic LEDs as well. So I think the possibility of using perovskites for light emitting devices is something that we are working on, and so are many others. So in my last slide, I just want to touch upon what are we doing going forward. We are working on tandems as well as BIPV. We are working on light emitting transistors and LEDs. Lasing is something that we have worked on. Roll-to-roll printing, we have not started yet. Hot carrier solar cells is definitely something to look at for the next 5 years. We have some of my colleagues have now published neuromorphic computing related publications, because perovskite is an ionic conductor as well as an electronic conductor. And lastly, the possibility of quantum devices is something that excites me as well. And with that, I thank you for your attention, and I'll be happy to take questions.
Thank you very much, Professor Subel, for this very, very interesting talk. And I see several questions. Maybe I can ask only few because of the limitation of the time. One question is by Dr. Kanan. Since the evaporation is a high temperature process, do you think it would be a limitation while using organic perovskite material with lower temperature stability?
It's really, depends on what you call a high temperature process. For the lead iodide, we are using in excess of 200 degrees centigrade. But as you have seen, we have deposited this on plastic substrates as well. And I really don't see a limitation in terms of the evaporation temperatures. If you are referring to, can you deposit cesium, lead iodides and bromides? The question is yes, but the efficiencies of cesium-based cesium lead bromides is not as high. So that is something that we need to work on, and we are looking at that. So from that perspective, this would be future work. Yes.
Okay. There is one more question which I saw. I think you made some comment regarding the water splitting application using this perovskite.
Sure.
So can you make some comment on that?
So really, we have shown both, not me, but my colleagues have shown both types of devices where this has been used because of the high VOC. This really can be used almost directly for the water splitting applications. Of course, in situ water splitting is a different concept. This really is using the VOC to drive the water splitting process.
Okay. Okay, so there are more questions, but because of lack of time, we have to stop here because the next session will start at 11 o'clock. So thank you very much for your good talk. You have really shown that stability is the issue and the high efficiency is the issue. And with your research, you really have achieved both of them. So it's a very good achievement, I would say. Thank you very much, Professor Subodh, for giving this invited talk.
Thank you, my pleasure.
So thank you very much. So now I think the all parallel session will start from 11 o'clock. So you can the delegates can join to different hall for their parallel session on different subtopics. Thank you very much. So we end this session here.